All right, so let's dive into this demo and see how this looks, how you can do this, handwriting recognition example, and how this, ends up looking when we do this. So I'm going to pull over my VS Code editor here. So VS Code is a great environment for working with Julia code. It's a really nice, IDE in general, but it's also kind of your entry point to running code on JuliaHub. So I have a very simple example here that does this MNIST classification in my editor. And the a few lines of code here belies some complexity, but that's intentional. I include my model definition. I simply train it and then I test it. And that's it. That's all that's going on here. I set some outputs and a results file to upload. These are ways that I talk to JuliaHub and kind of how I set up my pipeline to make sure that I can see what's happening. So really, there's just 3 lines of code here. But of course, the beef of the matter, the bulk of the matter is happening in this model.jl file that I include and define. And if we jump over here, you can scroll down and see where we build our model. Let's see, where is that here? Here it is. So this is the model definition, and this is a standard Flux model. That's just a chain of layers, right? That's kind of, even if you're not familiar with Flux and the machine learning framework that it provides, hopefully this chain of many layers here looks somewhat familiar to you if you know machine learning. If you don't, that's just fine, but this is how you define a deep neural network with many layers, where we have convolutional layers, a pooling layer, a convolution, and so on and so forth. And this is, how you would do image recognition. And the bigger and the deeper of a network that you have, the longer it'll take to train. Now, if I were to run this on my own computer, right, I could pull up in VS Code here, I could pull up a Julia REPL, start a REPL here, get things going, and run this train model, right? I could just work my way through this train model, time it, train it, and test it, and so on and so forth. This is a large model that I'm wanting to train, and so the way that I want to do this, if I were to do this on my laptop, I should say, it would take probably an hour to 2 hours, which is a long time to wait, right? And that's because my laptop doesn't have a beefy GPU that I can lean on. It's just a typical Mac laptop that doesn't have a general purpose graphics processing unit, which means a GPU that's been repurposed for general computation. And this is really important for machine learning because machine learning algorithms can lean on GPUs in a significant manner that allows you to speed up your algorithms and your training, importantly, 10 to 100-fold. And so that can be a huge, huge time saver here. So what I want to do is I want to use JuliaHub to deploy this model and to run it. There's a question just kind of how this model file is included, how does the web loop work? And I'll show that to you once I've trained this, right? The first step is to just figure out what the guts of that neural network should be, what all the weights should be, and how that should work. And the way to do that is to pull up JuliaHub. And as part of VS Code now, you can also install a JuliaHub plugin that allows you to connect to the cloud, essentially. And it makes your laptop or whatever desktop computer you're using kind of like the head node of a cluster. It allows you to kind of define these things, get them set up and running. So that means that I don't need my local Julia REPL anymore. I can hide this. And instead I have this job configuration pane on the right here that allows me to see, exactly what file I'm going to use. And you can see that it figured out that I'm working on this train file within this MNIST demo. The handwriting recognition data set here is called MNIST. And I can set up my cluster in the cloud to figure out how to deploy this. And you can see here there's lots of ways to play with these sliders. You can choose how much memory you want each machine to have, how many cores each machine should have. And kind of what's cool is you can choose how many machines should all be connected together. And so you can very quickly build a cluster in an ad hoc manner here that just gets these things set up and running. Let me close this notification here. And this model is set up to use GPU acceleration if it's available. And so I can hit GPU here, and now I have two different GPU configurations. I'll use the beefier of the two GPUs. I don't have things set up for distributed compute, that is more than one machine, and that's just fine. I can just have this set to run on one machine in the cloud that has a GPU. And that's beneficial to me because I don't have a GPU locally. You can see here, I know that this shouldn't take much time, and it'll cost me $450 if this were to run for an hour, and I can kick off this job here. So I just hit start job. What it does is it goes in, it figures out, it looks at what my script is that I'm working with, figures out all the dependencies that there are. So that includes this model file. It knows that that is a dependency, and so it'll upload that, get that model file. Let's pull that back up. And in this model file, it also will, let's see, come on, there we go. It also will see all of the packages that I'm using. And here I'm using the Flux package, right? That's the machine learning framework, a bunch of other packages, and including the CUDA package, right? That's the GPU programming package. And so it knows all of these dependencies, bundles them all up, and this will even catch private package dependencies. In this case, I'm only leaning on open source packages, but it'll also work just as well with any local packages you're developing, or private packages that you have registered within your company that can find that code and run it just as well. And this all happens seamlessly. And in fact, if you go down here to where we're doing our training, you can see how I've set this up for GPU computation. It's just a matter of calling this GPU function. And if I were to run this locally, this is a no-op, right? I don't have a GPU to move my data to, and I don't have a GPU to move my model to. So that just doesn't, doesn't end up happening. It just doesn't do anything. But if I'm running it on a beefy computer in the cloud, say, that has a GPU, well, then it'll be able to move our data there. So that's how this is working and what's happening. I started that job. And if I go back to my JuliaHub panel here and scroll down, you can see that I have some logs, some status of what all is running, what all I've done. This job that I just submitted here, it's currently running. I can check in on its logs. I can go here and just click this live button. It'll pull up a logs panel that has all of the logs that are running through the system, and I can watch its progress as it goes. It's right now waiting for the machines to boot up, making sure that they happen. I have just kind of to speed things up and allow just a smidgen of time travel. I have a video of what this looks like as we go through and do this. Let me pull that video over here. And we can, this is what happens, as you're working through. So this is real time right now that I'm playing this video, and you can see that it goes in, finds all the dependencies, sets up all the dependencies on all the computers that you have. In this case, we just have one computer, right? We just have that one computer in the cloud with the GPU on it. And so it's going in, installing all those packages. Let's skip ahead a little bit in time here. It downloads the data, gets it all set up, loads up the data. Skip ahead a little bit more. If you can see the little timestamps here, it's just been 5 minutes that this has been running here, that it's now training the loop, and each loop of the training system here is showing the test accuracy, saving the model incrementally. That'll get uploaded as its result file, and this is looping through my data set and testing it. Now, what's really cool is I can scroll back up to the top here, and watch this happen on a graph in real time. And so anything that I'm logging, I can graph. And this graph is live of all the logs and whatever I set up in my program. In this case, I've set up to log out the epoch number, so the iteration number of my job, and the accuracy, the test accuracy that we're seeing. So you can see we started off after one epoch, we're actually doing surprisingly well with somewhere around 97% accuracy. But after about 10 or 20 epochs, we seem to be saturating our job here and find the best accuracy that we have. And we actually save out, this code is set up to save the best one here, which is 99.3% accuracy. So that's how this looks, right? And this is a really cool, really powerful technique for you to watch your jobs in the cloud as they go. You can see that this only took me, about 10 minutes to run this job, which means that it only cost me, about $1 to run this in the cloud, which is pretty cool, right? You can compare the costs here. And actually, if I were to have run this on a normal CPU machine, it would cost me, about $2 because it would take so much longer. That even though the CPU machines are cheaper, it allows me to, get my job done faster and cheaper by using the best in class kinds of things that you have here. So this is how a single node job looks like. Let's hop over to JuliaHub.com, just kind of see what this looks like in practice. So I have a website here. This is the JuliaHub.com, and you can actually go there. We just flipped the switch this morning that allows everybody to run this code. So we have documentation on how to do this, how to get this set up, and how to follow along with me. But all it takes here is to create an account and log in. And once you're logged in, all you need to do is set up a credit card that'll get hit. So I have my credit card set up here. You can set a credit limit just to make sure you don't exceed some, some maximum amount and make sure that your jobs are fitting within your budget. But in general, this is very affordable. I can go back to my run code section here and see, a little bit of details about how this looks. So here's this job that I just ran this morning, and how this is set up is this is the job that I just ran. This is the job that is still currently running here. I can click on details, and you can see, the things that I've chosen to log, the amount of time that it took, the number of epochs that I ran it for, and the accuracy here. And this cost me just a little over $1 to run this example. Now, if I go down here a little bit farther back, I have a version that I ran without a GPU. Where is that here? Going back a little bit more in time. Here we go. So here's a version that I ran without a GPU, just using the smallest machine that we support in the cloud. It's just a 2 CPU machine with 4 GB of memory per CPU. So it's kind of your baseline machine. It took, instead of just 300 seconds, it took 3,000 seconds. And that meant that the cost is more here. Even though the cost per hour is significantly less because we're not using a GPU, you can get your job done faster using the GPU parallelism here. So that's how this works. So let's move to an example where you would want to use multiple machines, and you'd want to use, really exploit the capability of the supercomputer in the cloud, the ability to run your code in the cloud. And with that, we can look at a much bigger task, a much bigger problem. And a great example here is AlphaZero. AlphaZero is the machine learning model, the framework that Google's brain division used to beat the best human player in the world at the game of Go. And they did this about 4 years ago. And at the time, it was thought to be impossible. It was thought to be still 10 or 20 years out that a computer would be able to beat a human at the game of Go. And they did this precisely by leveraging compute. They did it by combining training and search, sort of learning and search. And those two things are two things that computers are really good at. This is kind of the way that the Go board looks. You have lots of branching, right? There's many, many, many hundreds or even thousands of moves that you can make on each turn. And of course, that expands out exponentially to just an intractable number of possibilities to search for. And so they use a neural network to learn a little bit about the board state, learn what branches of this huge tree are worth searching, and then tests out, searches them all. And both of those tasks lean heavily on compute. And so you want to be able to use this compute and be able to express your algorithms in a way that you can really lean on compute a lot. And the way this works is it all leans on Julia's parallelism structure. So in Julia, we have three main ways of parallelizing. On the left, there are GPU cards and GPU acceleration, which I demoed with the handwriting recognition example. In the middle are threads, right? I'd say get the best performance out of a single machine. We have really awesome multi-threading capabilities that are now no longer experimental in Julia 1.5. And on the right is a supercomputing cluster that has many machines connected together and all connected working together. And to do that, we use the built-in distributed standard library. And so these are all core components that are part of Julia itself, and we've wired them up to make sure that we have these available to us, and we can use them in JuliaHub. So the way that this works is I can go back to my VS Code here, pull up my AlphaZero example, and it's the exact same idea, right? I want to use I have my file here that sets up my AlphaZero board, includes all the things that I want, sets up things to run and trains. And this looks very similar to what I was doing before, right? It's just a little bit more complicated to set up the session, figure out what kind of game we want. We're going to use Connect 4 as our game to demonstrate this, to play with it. And you can see how that works here. And you can go in and see how it saves its intermediate values and plays with this. And we just, as when we finish things up, we do the same sort of thing of uploading the file, but this time AlphaZero is a much more complete example of how things work. And it doesn't just save out the model weights like our MNIST demo did. It creates an entire folder that describes the session of what we did. It has some incremental plots, has some things about how that works and the way it looks. And so you can play with this, see how this looks, see how it works. But the idea is the exact same thing. So we can connect to JuliaHub again, and connect to this, and hopefully now you have a better idea of what's happening here. It's connecting to the JuliaHub server, just like we did last time, and it's connecting as me, which is important because it's me who has my own credit card information set up there and has this set to use and to work with. But just like last time, it's figured out what the file should be using, how it should be working, and we can set this up just as easily as before. We're going to use many machines, right? And we'll want to have 8 threads per machine, so 8 cores per machine. We'll set up, in this case, let's just use a handful of machines, maybe about 10 machines here. And you can set up how many machines you want, 8 cores each machine. And then we can choose whether we want our execution model to be a process per core. So that is, if I had 10 nodes here, 10 nodes of 8 cores, and if I'd used process per core, that means that Julia would launch 80 processes total, and connect to them all using the distributed standard library, get them all wired up, connect correctly, have all the dependencies in the correct place for all 80 of them, and get them ready to talk to each other, and then run your code, right? But you can also set things up in a process per node fashion. And what this means is that we'll only have 10 Julia processes total, but each Julia process will be able to use multi-threading and be able to access all 8 threads. So essentially you have the same computational resources, but this is structured a little bit more friendly to the computation and allows you to exploit computation a little bit better, and reduces a little bit of overhead, because multi-threading overhead is less than distributed compute overhead. It kind of makes sense, right? You're talking to many threads on the same computer as opposed to reaching out to lots of computers. And so the execution model reflects that a little bit nicer. But again, we want to use multiple GPUs. And the way AlphaZero is set up here is that we can set up a beefy GPU. These GPUs will have 8 threads. We should note that in this UI at some point here soon. But each node has 8 threads, and AlphaZero uses all 8 of those threads to bundle up work and send it off to the GPU. And so we have 10 nodes here. Or let's set up 11 nodes, and those 11 nodes will bundle up work, split it across the workers evenly, and then each worker will use all 8 threads to churn away at the search, the learning and search process, and bundle up chunks of work that the GPU can churn on. And so one of the constraints of GPU programming is you need a beefy enough program, job for the GPU to do, and you want to batch together your work so that way the GPU can do lots of things in parallel. And it works really nicely, actually, to use many threads to bundle up work for the GPU, then kick it off to the GPU and get things going. So this is fully what's called heterogeneous compute, and this is one of the workhorses of HPC compute in general, is the ability to do things like this, where you divide up your work across many machines, across many threads, and across many GPUs. And so you have 3 different forms of parallelism, all built into Julia, all extraordinarily solid ways of expressing your jobs. And you can see here that this is going to be a more expensive job, right? It's going to cost me on the order of $50 an hour, and it'll take me about 2 hours to complete. I know this because I've run this before and can go back and show you how this works. But again, kicking it off is just the same way to do here. Now, if I were to run this on my own laptop, this would effectively be intractable because I don't have a GPU. If I were to find a GPU machine laying around my office somewhere, and run it on that, so if it's a relatively modern GPU machine, it'll probably take about 10 to 15 hours to complete, depending upon the machine itself. But by spinning up 11 of these workers in the cloud, well, I can make use of that, get my answer a lot faster. It'll cost a decent amount, right? This is a beefy compute task, but I can kick this job off, run it, and get it going in the cloud. We can look at what that looks like here once I've run things, and we can see as you go to this, you can go in and download the results. So I'll go back to JuliaHub here, where you can get the same UI and download these results and extract them out to a folder that you want to use. We're improving this workflow here, and once it's extracted, you can go to the file browser. Right, we've bundled up all our work, all that job that I've submitted, 2 hours worth of work across so many machines. It's all bundled up here for you to introspect and look at and see, and including plots. Right, so the workers can save plots, and you can see how many iterations we did. So we did 10 iterations, and you can watch how the computer learned to win at Connect 4. And after about 5 iterations, it was doing pretty well, right? Winning nearly all of the games. Of course, even more fun is the fact that I'm using this locally, and so I can play against the computer, right? This is a game, and what better way to test your machine learning algorithm than to play a game against the computer? And so I've launched, alpha0.jl includes some fun little UIs like this, where you can see the Connect 4 board state. You can choose to play blind against the computer. You can see the computer's, chance or, probabilities of what's the best move given what's happening and how things go. So lots of depth here to play with. But the cool thing is that, you can do this in a relatively short order, and it's not too expensive to do a huge machine learning model like this. And so JuliaHub allows you to scale. I can even then go in, change some parameter, rerun it, see if it's going to, set up the cluster config just the same as the way we did before. Rerun this, get things going, and how you can do this. So that is the crux of this. Is a question about how how does the code work with, how does this work with, when you're selecting this, we're not necessarily changing anything about our algorithm when we choose how many nodes we want, choose how much we want to use. We're not really changing anything about the code itself. And that leans on how Julia's parallelism intrinsics work, right? The way all of the threading infrastructure works, the way all of the distributed infrastructure works is that it just automatically scales to however many threads there are, automatically scales to how many workers there are. And so, the code knows how many workers are running and can distribute across all of them. And it's very easy to set up, and by default, that's exactly what happens. You do a PMAP or a distributed map reduce, and it'll automatically send out to all of the workers that are there. And so that's how it can be kind of agnostic to the cluster design. And so the cluster design is removed from your code design, which allows you to design your cluster to your economic limits and design your code to the best algorithms there are and the way you want to do that. And so that clean separation between these two panes allows you to a lot more freedom in what you do. And the key way that I debug JuliaHub and debug remote jobs is you start small, right? You just have a single node job and reduce the number of iterations, say, and you play with it and make sure things are working before you commit to a $50 spend. Yeah, I guess the last thing to note, and perhaps the most important thing here, is that we're giving everybody $25 worth of free compute to test this out. We want folks to use this. We want folks to try it, and so by signing up, you get access to $25 to play around with. Get some understanding, gain some familiarity, and report bugs back to us. Make sure that we get this as robust as possible. So thanks everyone, and hope to see you on JuliaHub.